Good evening, everyone. It's a short week, and I'm going to be using a screencast instead of the Movie Maker. We'll see how that goes. This week is just the properties of waves. We started to talk about the properties of waves last week, so now we're just going to go over the four main properties of waves and what they mean. So, first up on page 82, we have amplitude. Amplitude is the height of the wave. Simple enough. This dotted line here refers to the rest position of the medium. So if this band were just a rope or a band and there was no energy put into it, it would be flat, resting there. But if we put energy into it, the energy will travel through the band as a wave. Now, the amplitude is how high that wave gets. The useful thing about amplitude is that this height determines, or maybe I should say it shows, how much energy was put into it. The more energy is put into the medium, the higher this amplitude will be. Conversely down here. So, amplitude is the measure of the crest from the rest position, and it also shows the energy of the wave. So, we'll move on to page 83. And here we will see wavelength. Now, wavelength is correlated to the amplitude. But first we need to look at what wavelength means for the two kinds of waves, longitudinal and transverse. Now remember, longitudinal is like a slinky or a spring, and is also what sound waves are. So the wavelength on the transverse wave, it's easier to see. It's the distance from one crest to the next. One crest to the next. Or it could be one trough to the next. Now it is not the measure of an entire cycle of the wave. It's one to the other. But that is the wavelength. So up here, wavelength on the longitudinal wave is equally crest to crest. But remember, in a longitudinal wave, the crest is where there is compression until the next area of compression. With this in here is the rarefaction, would be this down part. So it's crest to crest, just like crest to crest. Now, if you can imagine that this is a band, you will also see that if the amplitude is increased, if this goes higher, that means that you will need to pull this up and this down, which will compress the entire wave. So, if amplitude increases, wavelength decreases. That is an important correlation in the properties of waves. Remember, the wavelength decreases, that is because the amplitude or the energy has increased. So, shorter wavelength equals more energy. And conversely, longer wavelength will equal less energy. And finally, frequency is a measure of how quickly the waves are occurring, basically. So we can here we can see a person on the ocean. Frequency is just a measure of how often the waves pass. It is also correlated to energy. More energy will result in a higher frequency, less energy, less frequency. So as you can see, all three of these properties, amplitude, wavelength, and frequency, are related to the amount of energy in a wave. Higher amplitude means more energy, lower amplitude, less energy. Higher amplitude means shorter wavelength, so shorter wavelength also equals more energy. Conversely, a higher wavelength, or a longer wavelength, I should say, equals less energy. So, higher frequency also equals more energy, and a higher amplitude with a lower wavelength. all of these are correlated. Now, it's 3 different factors, so it can be a little complicated, but we will go over it in class, but it is important to remember. I'll say it one more time. Amplitude. Increased amplitude, decreased wavelength, increased frequency. Okay, so now we're going to look at the electromagnetic spectrum. Now, here we have the electromagnetic spectrum. These are the waves that do not need a medium. They travel through empty space, but as you can see, we still have waves. Now, as you may notice, these waves here have a longer wavelength. These waves here have a shorter wavelength. Now, if you remember correctly, the wave with the longer wavelength correlates negatively to energy or amplitude, so that means that these have less energy. So we get to the right and the wavelength becomes shorter and shorter. That means more and more energy. We do call these long waves and we call these short waves. If you're worried about dangerous kinds of electromagnetic radiation, the short waves are dangerous and the long waves are not. So now we're going to look at some of these. As you see here, it says radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma ray. So the radio waves are our typical cell phones use radio waves. So a lot of people talk about the dangers of cell phones, but they are actually the longest waves that there are. So if there is a danger, it would have to come from using a whole lot of them, because they are the weakest waves that we are aware of. Also, the radio tower, radio signals, cell signals, they all take advantage of these radio waves. Now, we do use them in great abundance, but logically speaking, they are the longest wavelengths that we know of. Therefore, they have the least energy. Therefore, you would think that they were the safest, which is why we use them for so many of our communications. It would be very unwise to be sending all of our wireless communication signals around on gamma rays. That would fry everything. So, we also have, let's see, microwaves are next. Microwaves are a little shorter than radio waves, but not really that much. It is a concentrated tuning of them that creates the heat in here, so you obviously wouldn't want to, put anything alive in there because it will cook them, but microwaves in general, still not that powerful. And then as we get shorter than microwave, we come to the infrared, which this is a pretty cool picture of just what we would look like at infrared. Over here is temperature. The human body temperature is right around here, so it's this between yellow and orange kind of color. As you see, your body is emitting that color, a normal person. Maybe you've gone through airport security where they test to see if you have a fever and your temperature is up around here, they'll start to see white. That's what that's about. They're using an infrared camera to get a measurement of your body temperature. So you see these things in the background, the wall, much cooler than our bodies, the environment usually is. So that's just infrared. Less energy than the next one, which is visible light. Everything that we use to see, our eyes, are using electromagnetic waves that have more energy in them than the infrared, microwave, and radio waves. And that's what we use to see. That's what our eyes are exposed to our entire lives. How we see everything we see. So, more energetic than all of this. And then, as we start to get more energetic than the visible light, we come in contact with the UV. This is the what can damage your skin over time if you are out in the sun for too long. Here in the tropics it's a little stronger than in the northern latitudes and southern latitudes, but still just barely stronger than what we can see. And then moving on, as we get shorter and shorter, we come to X-rays. These are very strong. You can get an X-ray and the amount of radiation is significant, but if you're not getting an X-ray every day, it shouldn't be a problem. However, X-ray technicians who work in a hospital or in a doctor's office, that's why they stand behind shielding, because they're taking several of these things every day, and it will add up. And there are some reports even say that some people who maybe over the years have gotten dozens or maybe even hundreds of X-rays can start to cause problems. But one X-ray, no problem whatsoever. 2 X-rays, not a problem. If you have 5 every year, not a problem. If you've had 100 this year, maybe time to start to worrying a little bit. And then after X-rays, we get to the strongest or the shortest waves that we know of, which are called gamma rays. Their wavelength is barely the size of the center of an atom. Let's remember how small those are. But because their wavelength is so short, they're capable of disrupting that atom. Gamma rays are capable of tearing apart matter. That's how much energy they have in them. And that is why we need to be very careful. One of the first well-known sources of them was released in the nuclear explosion. And then, conveniently, we also notice them coming from space. These are the cosmic rays, and this is what's dangerous about space travel. Mission to Mars, one of the most difficult challenges to overcome is the exposure to this cosmic radiation. Now, our atmosphere and the magnetic field around the Earth is protecting us from this. You go out into space, no more protection. You're being exposed to the strongest kind of waves there are. And there's a lot of work being done with the astronauts in the International Space Station and studies on their exposure to this, and they can't be there that long, and a lot of interesting results. So, in class tomorrow, we are going to look at a lot of the technologies that we use. We're going to look at one of the attributes of them, and from that you should be able to tell me about the other 3 characteristics and how safe or dangerous they are, or how energetic they are, something like that. So it's important to understand from long to short radio, or from long to short waves, and what that means for their other characteristics. Alright, see you in class tomorrow.